With the transmission system, you solved it and then you got this voltage, right? That voltage is in our case voltage on bus number 3. After you complete the power flow, you will get a voltage here, right? You will be getting that voltage. And what is that voltage? You have that number? I don't have probably. Or 9716 something. Or 047006, something like that, right? You take that voltage and then run your forward backward sweep. So this voltage is, if you do the forward backward sweep, I think there is something that we did not do. I don't know, we did not do. We used 2400, right? We did not convert into per unit. Remember, I think we did actual. Better to convert in per unit. So 2400 will become 1. So with 1, we did the forward backward sweep. Instead of 1, you should do with this thing. Once you do the forward backward sweep, you will get this P plus JQ, right? I'm calling this P plus JQ as P1 plus JQ1 superscript. This is some number before. We run that, you got this P1 plus JQ1, right? Good. Make sure, makes sense? I'm going to write it here. Step 1, run transmission system power flow, find voltage on bus 2. Step 2, keep that voltage for distribution system station. Step 4, run forward backward sweep with this voltage. Step 5, calculate power from substation. Okay, I'm going to repeat it. Step number 1. If you're not cannot read my handwriting, also you can see. Run transmission system power flow. Find voltage on bus 2. Step number 2. Keep that voltage for distribution system substation, which is this. Run forward backward sweep with this voltage in the distribution system substation. Calculate the P plus JQ from substation. From where? From forward backwards sweep. Multiply the power to get transmission system bus 3 power. What do you mean by multiply? Take that power, suppose this power is 3 and this power is 13. You multiply 3 times 4 to get to the power which is close to 30. Right? With the same, just a nominal number, 4 times, 5 times. Don't have to do 4.53, 5.63. No, don't have to get exact. Just to do a nominal. And then repeat step 1, which is basically run transmission system power flow, find on bus voltage. Is bus 2 same, bus voltage on this 2 same as before or very close? Same meaning a small number change. If yes, stop. If no, repeat. That's your try that and we can look at it. I think you should be able to do it because we did both powerful. If you have any question, keep asking. Okay. If not, then can work. But
in our major project, we are just have to make a like if we want to make a electric vehicle charging station solution. But for that, we have created this model.
So modeling that how to model this design and simulation of a cost optimized solar grid EV charging station with basic smart schedule.
Design and simulation of a cost optimized solar grid recharging station with,
Basic smart schedule.
yeah, so smart scheduling. So you are scheduling the output from the EV charging or the smart devices, whatever is connected, based on a objective. The objective is cost optimization. Cost. So what you do is you run a cost optimization algorithm, okay, which is,
Make a EV charging station
yeah.
which can use fully and making power and then from
Yeah. So the cost optimized model will be at that time reducing the power from the grid. That is basically the cost of. So what you do is that you look at what is the power from the grid. You look the substation bus is a grid. So on the substation bus power is the power from the grid. So your cost of this model is minimize substation bus power from the, so minimize the summation of EG plus JQG um, for for a specific time, whatever the time. That is basically your so how do you minimize the power? Which is very simple. If you have one DG, think about it. Minimize the power on the substation bus. The one DG is to provide all the power from this. Then I think you minimize the power. So you have a EV charging station and you have a photovoltaics for battery connected at that point. Will continuously take care of the power from the EV charging station. Then there is no power coming. That's a good model. So what you do is that your PG minus PG has to be minimized. Means the P load plus P EV charging minus P DER minus P battery, all that should be equal to 0. Then it will. And why should. So you look at the, you think about the same drive which you have, at that point you have a EV charging, right? The EV charging power is taking power. Load is taking power. The PV, suppose it is giving power.
Yeah.
So that giving power, whatever is giving, I am assuming there is a battery too. Whatever is giving minus whatever is taking should be equal to 0. So minimum of whatever is giving minus whatever is taking. Sum of those should be minimum. That is objective. So you write a objective function like that. Then you write a constraint. What is a constraint? A constraint is all the power coming from the generated power should be equal to the load, all the load consumed. The constraints are similar. We did it. Then you run an optimal power flow. Optimal power flow, we have run an optimal power flow. You got to know how to, I mean, you know that, right? The equations and run an optimal power flow. Run an optimal power flow like that. Forget about scheduling the EV charger. Run an optimal power flow just like that and see what will be the reduction. It's a first step. Assuming that the EV charger is following it, right? So that's the first step. After that, how to implement it? To implement it, this thing has to go to the EV charger controller, and EV charger controller should follow, like what we are doing, implementing. That's a different. You are creating a box, but once first you need number and show that if you put that number, then the cost is low. Right? So that is so two problem. One problem is defining this algorithm for the optimal power flow, which we run it. After you run that, you look at to see what will be the reduction in the power. How do you look at? You run it on a model, assuming the controller is working. Then you look at what is the reduction. Then the third phase is how to make controller work. So you ask the controller. So some controllers are already there, like That may not be your objective because EV charging station as a controller, it gives us a point, the EV charging station. So let's assume that EV charging station connected to one place is charging, but you are not letting it charge fully. You are charging based on a power, so which means it charges less to maintain that power. That's for the EV charger. So which means it takes the power less. If your PV is connected there, it charges fully because it can draw the power from the PV. So it doesn't really matter. So those things are probably not your objective. That will be in the field you can implement it. Your objective is probably get that number, a good number. Sure. You follow what I'm saying? Understand? I don't know whether we have how. Well, I think we may have to do it tomorrow. I don't think in the tomorrow lecture we'll talk about how good are you on optimal power flow algorithm development. I showed it was more like a show and tell. You have not done it, right? I showed on the MATLAB and then you know just so tomorrow in our time morning I will take only 30 minutes of slide. For remaining 1 hour, you write to the optimal power flow. So maybe you will get an idea of the stuff. Because you're not written anything. I think this one at least you started writing, even though it's not complete, you get an idea. If you don't do anything, you will not do it. So I'll ask you to write. Yeah, you got it.
Now after that we have some data required for distribution system.
Yes.
What
What is the number that you got?
I got that even whatever is
Yeah, and that is not the same as the other load number, right? It's a different. So you multiply.
P and Q,
You multiply with a scale number.
you run it to the distribution system. What is that? Where
No, P and Q is from the distribution system. Voltage is going to it.
so voltage you get that voltage is where we
Put it on the substation. The 20 instead of 2400.
okay.
So 2400 angle 0 120 we wrote, right? Instead of 2400, it should be 2400 multiplied by 0.97, whatever
For
the
the same
voltage.
system we have to put it.
For the
Same that
2%. That one you put a 0.97. Let's assume 0.97. So you 0.97 multiply by 2400. So it will now be 2400. When you run, then you get P and Q from substation for the distribution network, the 2-bus system, not the last load, S load 3 or S load 2. Calculate the S load on the substation. Take that number, multiply with a scale 10 times or something to match with the load on the transmission on the second bus. Second bus load is 100 MVA, whatever that load on the match close to 99.9 or whatever that number, multiplied by single, and then run the transmission one again. There is one other item that we were talking just now, I gathered. Tomorrow, when you do your tutorial, I will let you work on a small example of optimal power flow. We talked about it. I showed it, but you did not do it, right? they're doing their tutorial, so they can stop anytime. So whenever you are ready, they can stop and they can continue as a take home. So I gave them the same topic as a take home, so they can choose. And tomorrow, I'll do a 20-30 minutes on the IBR control. And then I will do a 30 minutes of tutorial, 1 hour of tutorial for them. So they have more time for working on optimal paths. So we have from 9 to 11. That's our time. Yeah. So we'll do 1 hour tutorial and 1 hour on IBR. Then after 11 to 11:40 will be test. 11 to 11:30, I think 30 minutes. 30 minutes for the test. 11:30 to 12 will be grading. And then 12 to 12:30 will be conclusion. And the grading distribution or something certificate. Certificate distribution and closing. Closing. Right. 12:30 will, and then 15-minute buffer. No, it is 15-minute buffer. So 12:45, and then this is the target of 12:45. I will try to just go on that path only. Correct. Then maybe after 1:15 we can leave. That's enough, right? 1:50, 1:15, even 1:30 we will. Then 30 minutes, 35 minutes we will reach. And then you get 2 o'clock. 2 hours. So the check-in is not fast. It is not issue. Not any for domestic flights. Yeah. And for not for here, only domestic flight you will get, but there's no this is hassle. No rush. And I will use this side of the so that